A high-velocity surge of charged particles, racing at 700,000 kilometers per hour, is set to slam into Earth from an uncommon transquatorial coronal hole, precisely when the interstellar comet 3I/Atlas unexpectedly slips behind the Sun. Scientists label this alignment a prime coupling phenomenon. The magnetic portal stands ajar, enabling geomagnetic disturbances to flare up with minimal opposition. Simultaneously, a sharp uptick in intense seismic activity has researchers debating whether it's mere chance or a linked trigger. While some reject any ties, others suggest we're observing a broader celestial sequence taking shape. Authorities maintain that these occurrences remain unrelated, yet 3I/Atlas appears to be influencing our Sun in intriguing ways, and its return could upend established principles. The initial query revolves around the implications of such a massive solar outburst for our planet. A coronal hole isn't an actual breach in the Sun. Rather, it's an area where the solar corona grows sparse, and magnetic field lines extend freely into the void without restraint. Typically, the Sun's exterior confines its magnetic forces within compact, curved loops that contain scorching plasma. In contrast, within a coronal hole, these lines fan out broadly, resembling an unlocked entrance, which permits electrified particles to burst forth at remarkable velocities. Satellite observations depict these zones as shadowy, expansive voids that may cover thousands of kilometers, occasionally spanning from one solar pole to the opposite. A coronal hole that crosses the Sun's equator transforms into a transquatorial conduit for solar wind, linking the northern and southern regions while directing power straight at the orbiting worlds. The October 2025 occurrence started with imagery from SDO/AIA, revealing an exceptionally wide unipolar coronal hole that connected the Sun's two hemispheres. Magnetograms verified the field's negative and exposed nature, a setup uncommon beyond solar minimum phases. This expansive layout permitted a swift stream, reaching speeds of up to 700 kilometers per second, to erupt and speed across the inner solar system. Space weather specialist Dr. Tamay Siskov characterizes these areas as magnetic release points where the Sun's plasma doesn't merely bubble but erupts freely without barriers. The orientation and charge of this emission are crucial. When the Sun's exposed field aligns squarely with Earth, our planet's protective magnetic barrier must face a persistent, targeted onslaught. This dynamic forms the basis of what experts term the ideal coupling arrangement. With the magnetic barrier unlocked, the solar wind accelerating, and Earth squarely in its trajectory, the ensuing outcomes hinge on the interplay between these fields. Solar wind doesn't merely skim by Earth. Upon the arrival of a rapid stream, particularly one hitting 700 kilometers per second, our magnetic defenses engage in a head-on clash. The true intensity emerges at the interface where solar and planetary fields meet. At this juncture, the Interplanetary Magnetic Field, or IMF, serves as the connector. During October 2025, the IMF tilted decidedly southward, remaining stable around -12 nanotesla. This alignment proves vital since Earth's field orients northward. Such opposing polarities allow the fields to merge abruptly through a mechanism known as magnetic reconnection. This process opens the floodgates for solar energy to flood the magnetosphere. These interactions manifest in tangible impacts, variations in power networks, orbital drag on satellites, and strikingly, auroral displays extending into unfamiliar territories. On the evening of October 12th, shimmering veils of light danced as far south as Michigan and Maine, stemming directly from the seamless linkage between the Sun and Earth. The outcome is a magnetosphere charged for activity, where even typical solar wind levels can spark widespread responses in the upper atmosphere. Every surge in speed or flip in polarity generates waves across the planet's electrical network, paving the way for inquiries that extend far past the magnetosphere. 3I/Atlas stands out as more than a typical frozen traveler. As the third verified interstellar visitor, its composition challenges long-held assumptions about comets. Unlike most solar system comets, which rely heavily on water vapor, 3I/Atlas deviates sharply. Its surrounding coma is driven by carbon dioxide, venting at levels almost 8 times that of water. This trait echoes environments in the icy realms past Neptune more than native solar system origins. Observations via ground and space-based telescopes reveal a core under a kilometer in size, yet vigorous enough to eject matter at rates up to 4 kilograms per second. Even positioned 4 or 5 astronomical units from the Sun, it generated a detectable coma, a gaseous and dusty envelope created as solar heat warms the nucleus. The dust composition adds further intrigue. Rather than the tiny particles that form extended, luminous tails, 3I/Atlas produces bulkier, denser grains. Consequently, it displays a subtle, lopsided veil instead of a vivid trail. Its spin cycle, clocked at slightly more than 16 hours, aligns with the erratic, rotating behavior observed in other dynamic comets. However, the nuances of its surface makeup, abundant in organic compounds with an elevated carbon dioxide to water, what distinguishes 3I/Atlas truly sets it in a league of its own. As a mission scientist from SDO described it, this is like an envoy from a distant stellar realm delivering a formula we've yet to sample. The exceptional nature of 3I/Atlas goes beyond mere intrigue. It serves as a crucial experiment for understanding how interstellar compounds react to solar radiation and the potential revelations that could surface as it navigates its closest approach to the Sun. In the very same week that 3I/Atlas vanished behind the Sun and the solar wind pummeled our planet's magnetosphere, a series of magnitude 7 tremors shook monitoring equipment throughout the Pacific region. This coincidence sparked a surge of digital speculation, with some asserting that the solar flare or the comet's trajectory had provoked the uptick in quakes. However, a review against worldwide norms paints a contrasting picture. Data from NOAA's Space Weather Forecasting Hub indicates that our planet experiences about 15 quakes of magnitude 7 or greater annually on average. The recent cluster, though striking, aligns comfortably with typical patterns. No established seismologist endorses any direct tie between solar particles and crustal movements. Comprehensive reviews of long-term records uncover no consistent correlation between solar disturbances and seismic occurrences. Nevertheless, conjecture endures. Outlier hypotheses suggest interactions in the ionosphere or minor shifts in planetary spin, yet these ideas lack validation and fall beyond mainstream geophysics. As forecaster Michael Ryder from NOAA notes, proponents of such links bear the responsibility to substantiate them. Absent a verifiable process or evident statistical deviation, experts view these incidents as mere happenstance rather than cause and effect. This discussion holds real implications. It establishes the criteria for validating proof when bold assertions meet empirical findings. Beyond the Sun lies a range of possible results for 3I/Atlas. For primary scenarios, each marked by distinct indicators detectable in observations prior to the comet's reemergence. The most straightforward involves 3I/Atlas enduring perihelion without issue. Under this, the object returns displaying a luminosity profile consistent with earlier models, stable, possibly dimmed, but clearly following its anticipated course. The surrounding gas envelope stays contained, with no abrupt variations in its glow. Comet experts largely anticipate this result, though it promises the mildest spectacle. A different path entails breaking apart. In this instance, the narrative alters abruptly. Instruments like SOHO's coronagraphs, LASCO C3, Stereo ASHI 1, Parker Solar Probe's WSBR would detect a sharp rise in luminosity, frequently exceeding a full magnitude. Rather than one cohesive form, visuals could show a line of debris, a sequence of cores aligned along the trajectory. The particle haze widens, the envelope diffuses, and the tail might divide or curve. Historical examples such as C/2011 W3 Lovejoy and C/2021 S1 Ison exhibited these features: sudden illumination surges, forked extensions, and extra-luminous spots where none should exist. A sodium extension, uncommon, vivid, and golden, might intensify following intense breakup, visible through LASCO's refined sensors. Another option is quiescence. Here, 3I/Atlas reappears, yet its vigor has waned dramatically. The gas envelope contracts, the tail diminishes, and the core looks nearly point-like, subdued, indistinct, and potentially obscured by solar brightness. The light profile falls short of projections, and earthbound scopes might fail to spot it entirely. This echoes the fate of various dim sundivers, yielding a comeback so subdued it's almost undetectable, detectable only by vigilant analysts noting irregularities in readings. The most theatrical end is complete dissolution. Then, 3I/Atlas simply does not return. Absent any remnants in the coronagraph views, no debris, no surge, just an empty space where the core ought to materialize. Clues might include a faint particle path or a fleeting, unforeseen luminosity peak as the body evaporates. Every possibility imprints a unique trace in the observations: a luminosity surge, a sodium burst, a debris chain, or outright absence. As fresh visuals arrive, these markers demand attention. The search kicks off with one key frame. Soho's LASCO C3 coronagraph delivers its newest image to the RapidView repository. At intervals of 12 minutes, another view emerges, pored over by global comet trackers for traces of 3I/Atlas in every detail. The initial clue might manifest as a dim glow, an abrupt shine, or a minor warp in the sun's backdrop. Should the feed reveal oddities, like an unforeseen peak, a fresh piece, or a sodium glow, notifications spread swiftly across the Watcher network. Automated scopes then assume control. Setups, such as the Zwicky Transient Facility and Pan-STARRS, stand ready to scan the zone once 3I/Atlas clears sufficient solar interference. These systems image vast sky sections per shot, highlighting deviations from stellar norms. Nightly, their software contrasts new captures with celestial directories, marking movers or variable illuminators. Upon spotting a prospect, light measurement routines activate. Teams gauge its radiance and magnitudes. Multiple detection methods capture data through various filters, recording brightness levels and hues instantly. A consistent, gradual increase bolsters the argument for a comet that's holding together well. An abrupt spike points to possible breakup or an eruption. Hobbyists in astronomy are vital to this ongoing effort. Equipped with good timing and a basic scope, home-based stargazers can validate or question initial findings. Photos they share quickly provide backups and fill in the blanks left by pro observations. Each confirmed observation gets documented with exact positions and luminosity, forming a linked record that follows the comet's comeback. This teamwork, driven by space probes, automated scans, and people's watchful eyes, underpins the hunt right after conjunction. The strategy works for any dim, swift object, and those techniques will soon be needed for the upcoming comet visible in our skies. Right now, all kinds of scopes, from robotic to manual, are aimed toward the edge of the sky, hoping for Comet 3I/Atlas to end the quiet. Over the coming 2 weeks, each clear dawn brings a comet into view eastward. It shines more vividly than urban folks might expect, though it's simple to overlook without knowing the spot. Dubbed Comet C/2025A6, or simply Lemon, it now moves across the stars of Cancer, appearing pre-sunrise and giving folks with just binoculars a special shot at spotting a dynamic fragment of the solar system. No fancy gear needed. Head out 1 or 2 hours prior to daybreak. Pick a location with an unobstructed eastward view near the ground, and sweep slightly above Cancer's well-known stars. Lemon's expected brightness sits at magnitude 4 to 5, clear as a hazy, spread-out spot, but not vivid enough for unaided spotting. In pitch-black conditions, the surrounding glow might resemble a gentle circular puff with a faint tail trailing anti-sunward. That tail is brief, perhaps half a degree wide and frequently hidden by dawn light, yet binoculars uncover its gentle shimmer. The schedule is key. The following 14 days peak as Lemon ascends daily while the moon remains sidelined. Come mid-November, it'll dim and edge nearer the sun's brightness, so this period offers the prime opportunity for novice comet spotters. A standard 7x50 or 10x50 pair, whatever you use for sports events, handles it fine. Even from light-polluted suburbs, you can see it if you target the precise area. Plenty of backyard astronomers carry charts or rely on mobile apps to locate it. Others schedule wake-ups at 4:30 a.m., brew some coffee, and head outdoors before dawn stirs. Spotting it turns Lemon into far more than a vague glow. It's a trial for grander celestial happenings ahead. A method to sharpen your vision for subtle features, grasp the sky's patterns, and connect with fellow enthusiasts pursuing these temporary guests through space. Each peak, be it casual or a detailed light measurement, contributes to the worldwide archive. The abilities you gain, interpreting the heavens, following shifting targets, timing your watches, will prove handy for the next comet or space wanderer. For the moment, the steps are straightforward: alarm on, binoculars in hand, eyes to the east. The solar system's staging a spectacle, entry included at no cost. Well, after Lemon vanishes from dawn views, the lineup of space happenings remains packed. Yet another comet, C/2024 R2 Swan, is gaining notice for traits surpassing mere shine. Early 2026 should bring Swan into binocular range. Its standout feature? An ultraviolet halo around its core. That's a hydrogen envelope first spotted by the SWAN tool on the European Space Agency's SOHO satellite. This unseen hydrogen veil, which flares in UV light, serves as a marker for comet composition. Spotting it shifted the strategies for studying the initial water vapor release in a comet's atmosphere, matching the brightness patterns of Swan and Lemon, tracking their waxing and waning. Let scientists unravel the concealed forces behind gas emissions, splits, and the gradual melting of frozen cores in sunlight. The data trails from these two will act as models for decoding far-off comets' actions later. But comets aren't the only highlight in the stars. 5 key moments emerge as markers for following the solar system's lively rhythm. From late October to early November 2025, global scopes will seek the reappearance of 3I/Atlas post-solar hideout. On April 13, 2029, asteroid Apophis will skim so near Earth it'll drop under geostationary orbit height. A close pass at 32,000 kilometers, observable without aid across Europe and Asia. September 20th, 2040, delivers a planetary lineup, dubbed a parade, with Mercury, Venus, Mars, Jupiter, and Saturn bunching sunward, presenting a remarkable spectacle awaits stargazers and experts in the field. Peering even deeper into the future, 2060 holds an intriguing possibility: the potential emergence of a massive comet, spotted in ongoing observations as a remote, sluggish body that could match the splendor of history's most famous comets. Meanwhile, by 2177, Pluto will finish its inaugural complete revolution around the Sun since astronomers first spotted it in 1930, a deliberate, grand circuit that encapsulates the whole contemporary chapter of planetary exploration. Far from mere trivia, these milestones serve as poignant cues that our solar system functions as a dynamic experimental realm, perpetually evolving and presenting fresh enigmas to unravel. The cosmic schedule lies wide open, and for those who tilt their gaze skyward, the roster of wonders keeps expanding. During the final days of September 2025, a coronal hole spanning the equator released a solar wind gusting at 700 kilometers per second, sparking geomagnetic disturbances and northern lights visible as far south as Michigan. Simultaneously, the interstellar visitor 3I/Atlas slipped out of sight behind the Sun, its destiny a mystery, pending observations in late October. Although observers reported a surge in magnitude 7 quakes, seismic archives indicate these groupings happen roughly 15 times annually, without any established connection to solar phenomena. Probes like SOHO, Stereo, and the Parker Solar Probe documented the key alignment period, yet their findings remain inconclusive on whether 3I/Atlas endured intact, broke apart, or fully vaporized. To date, no restricted documents reveal the comet's final status. Undeniably, though, the dynamic connections among solar dynamics, asteroid protection efforts, and amateur astronomy continue unabated. The ensuing phase unfolds in late October, as Earthbound observatories hunt for signs of 3I/Atlas's reappearance. As mission expert Dr. Tamasa Skov puts it, the Sun's story is written in data, not guesses.